So in this work, we look at how abstracting the mailbox when analyzing actor programs influence the precision of the analysis. So first of all, what is an actor program? It's a program that is composed of multiple actors. Here we represent an actor as a circle. It's basically a process. It's associated with a mailbox. That mailbox contains messages, and the actor can process messages one at a time by extracting it from the mailbox. When it processes a message, it can create other actors, it can send messages to other actors, and it can also change its own behavior. So this is the essence of the actor model, and we model this essence into an actor extension for scheme. So here we have an example program where we define an actor that represents a stack. Then we instantiate this actor, so we spawn a new instance of this actor. It will then create an actor which has the behavior defined above. And in this behavior, we see here we see that the actor has state variables, so it has a state variable representing the top value of the stack, and a state variable which is a function that will represent the rest of the stack. And initially, both values are false, that represents the empty stack. Then we can send messages to the actor. We first send a push message with a value that's given by the user. When the actor receives this message, it will execute the code that corresponds to the message. In that case, it will change its own behavior so that the state variables are updated. So the value, the top value is now the value that's been given by the user, and the rest function is a closure that captures the current top value and the current rest function. So this pushes a value on the stack. Then we can send a push message with as argument a displayer actor that will display any message that's received. When this message is received, if the rest function is not false, we will send to the customer the current top of the stack, and we will call the rest function. When calling the rest function, we will restore the previous value, the previous state of the stack. If, however, the rest function is false, that means the stack is empty, we cannot pop from the empty stack, and we raise an error. So that's the kind of program that we want to analyze. We want to analyze these programs to verify absence of error first. So if we have this stack actor and we push a value and then we pop, it's a safe usage of the stack, and we want analysis to be able to prove that this is the case. If, however, we invert the messages and we first pop and then push, then we want the analysis to not be able to prove that this is a safe usage of the stack, because it isn't. We also are interested into verifying bounds on mailboxes. So suppose that we have two actors and their behavior is the following. So when actor A receives a message, it processes the message, it sends a message to B, which has the same behavior. It receives the message, it processes it and sends it back to A. If we know that this is the only message that can appear in the execution of this program, we don't need to allocate more than one element for the mailbox, so we can only allocate a single cell. And so we also want to verify this. So we are interested to detect errors and to detect bounds on mailboxes, or rather to verify the bounds and to verify absence of errors. How do we do that? We use an abstract interpretation-based approach. So we first start by describing the concrete semantics of the language. So this defines which program states are reachable in every possible execution of the program. Based on these concrete semantics, we can express the properties that we want to verify. So we have one property to describe the fact that an error is reachable if we have a program state reachable that describes an error. A second property describes that the bound on the mailbox of an actor is simply the maximal size that the mailbox of this actor can have under any execution. Unfortunately, these properties are not decidable because reachability within the concrete semantics of the language is not decidable. So we have to approximate. So we describe abstract semantics of the language, and then we can update the properties, and we can then verify these properties. So in this presentation, we will focus on how in the concrete semantics we can mitigate state explosion for static analysis by using macro stepping, a special form of it. We will then look at the abstract semantics and how we can abstract the mailbox and how it influences the analysis, and we will evaluate the work in terms of soundness, performance, and precision. So first of all, the concrete semantics. So suppose you have this program. We have an actor 1 on the left, actor 2 on the right. We create two instances, or one instance of actor 1 and one instance of actor 2. And then now we are interested to know what's the possible reception order of reception of the messages in actor 1. So we'll run the program. We first send a message to actor 2. We can switch to actor 2, and actor 2 will start processing the message. And we are here. We focus on the fact that a single actor is executing at any given point in time. So actor 2 can send message M1, can do some work, can send message M2 to actor 1. Then we can switch back to the main actor and send message M3. So that's one possible execution of the program. But there are other executions. For example, we can, from the same, send the start message, keep on executing the main actor. We send the message M3, and then we can switch to actor 2 and send message M1, perform some work, and send message M2. So that's a second possible execution. There is also a third one where, while performing the work on actor 2, we can switch back to the main process. And actually, if this work function takes multiple steps to execute, we have a huge number of possible interleavings at any point in time during this work function. We can switch back. So if we want to build a static analysis to verify a program under all the possible interleavings, that will be a huge number of interleavings to take into account. So we want to reduce this number of interleavings. But you are still interested to correctly approximate all the message interleavings. So one technique to mitigate this is to use macro stepping. So that has been defined by Aga in '97 as a way to ease the reasoning over actor programs. In that case, we treat the reception of a message and the handling, the execution of the body corresponding to it as a single unit of work. So we can execute this block of code atomically. So in that case, we don't have to investigate all the possible interleaving with the work function. So we describe much less instruction interleavings, but the problem with this technique is that we also miss message interleavings, and that's something we want to avoid. So in the paper, we describe a different version of this macro stepping, which in this case, the atomic step is only allowed to send one message. So we will only execute this part atomically, and we will still account for every message interleavings while diminishing the number of instruction interleavings. So this will simplify the analysis. So once we have the concrete semantics, we can abstract them. There are usual abstract interpretation technique on how to do that, but the work doesn't focus on how you can abstract the mailbox. So mailbox is a sequence of messages, and we show that depending on how you abstract it, this will influence the precision of your analysis. So for a safe usage of a stack, for example, depending on how you abstract the mailbox, you may be able to verify that this is a safe usage of the stack, or you may not be able to verify it. Let's look at a simple abstraction. So we have a set abstraction where we abstract the sequence of a message as a set. This abstracted mailbox corresponds to the concrete one, but it also corresponds to other mailboxes. For example, we have a push followed by a pop, followed by a pop. So because we don't have information about how many times each element is stored in a set. So we lack multiplicity information. If we add this information into the set, so we cannot verify the program with this abstraction, we add multiplicity information to the set that gives us a multiset. We know that we have exactly one push message, one pop message. This corresponds to a concrete mailbox again, but it also corresponds to pop followed by push because we have no information about the ordering of messages in this abstract mailbox. So again, we cannot verify the program. We have multiplicity information, but we don't have information about the ordering of messages. If we look at different abstractions, so we have abstraction that preserve ordering or do not preserve ordering. For example, the powerset does not preserve ordering, and it also doesn't preserve multiplicity. The multiset adds multiplicity information. We can have a bounded list or a list abstraction to preserve both ordering and multiplicity, and we see an empty spot. And we describe this as a graph abstraction in the paper. And with this abstraction, so how this, we'll see first how it works. So it's quite simple. So when we push an empty element on the mailbox, when we enqueue an empty push element on the mailbox, we have a node corresponding to the message. We have a front pointer. We have a back pointer. If we enqueue a pop element, we enqueue in the back. So we add an edge between push and pop, and we update the back edge. If we now dequeue an element, we dequeue from the front. It's pretty simple up to now. If we go back to this mailbox, and we know, so we enqueue push, we enqueue pop, and now we enqueue push again. We already have a push node, so we add an edge from pop to push, and we update the back edge, and now we have a cycle in this mailbox. So let's look at our stack example with this mailbox. We have push, pop. This is abstracted with full precision. It's very simple. It only corresponds to the concrete mailbox, and so we can verify this example. And in that case, we preserve both ordering and multiplicity. If we have an unbounded number of push followed by pop, followed by push, followed by pop, this corresponds to push followed by pop. It also corresponds to twice this and multiple pushes followed by pop each time. And with this abstraction, we know that every pop is preceded by a push, so every usage of the stack is safe, and we can verify this program, and that's because we preserve the ordering between the different elements. So we evaluated this work, so we proved soundness of the different mailbox. We have proved soundness of the analysis. That's all part of the artifact that you can find that you can find with the paper. We also looked at performance, so we have a number of benchmarks. For each abstraction, we ran the benchmarks. They came from different sources. These are still small, but that's in line with what the related work does. And we look at the number of states here. So we saw that in our evaluation, the number of states is linked with the time it takes to analyze the program. We have a 1 minute timeout here. And we see that, well, the less states we have, the faster the analysis is. And we see that the list and the graph abstraction usually produce the smallest number of states. We also mostly focus on the precision. So how did we evaluate precision? We compare the mailbox on the right, computed mailbox, the mailboxes that have been produced by the analysis, with the mailbox that can appear in every concrete run of the program. So here we have mailbox containing A's, mailbox containing B's. In the abstract, we will have, for example, with the set abstraction, mailbox, the set containing only A and the set containing only B. If we can, for each abstract mailbox, do a correspondence with the concrete ones, that's good. If we have mailboxes that do not have a corresponding element in a concrete run, we count this as a spurious element, and that's these elements we want to minimize them. So in that case, the mailbox in red is a spurious mailbox. We also count the number of spurious messages, so we have different types. So on the left, it's concrete. On the right, it's in the analysis. So that situation is perfectly fine. we have a concrete mailbox containing only the message A. A message that can be dequeued in this mailbox is the message A. In the analysis, we observe a mailbox, the set containing only A, and the only message that can be dequeued is message A. That's fine. If we have a spurious mailbox, we have no concrete element corresponding to it. Every message that is extracted from this mailbox is a spurious message. If we have a correct computed mailbox by the analysis, but we don't know, well, so in the concrete, we can extract only one message from the mailbox. In the abstract, we may extract more than one message, and the ones that do not correspond to the concrete one, we count this as a spurious message of the second type. And we counted all these spurious messages and mailbox, and we summed this result over all the benchmarks, and we see here how this sum over with every mailbox abstraction. So we see that the powerset abstraction has less, so it has more spurious messages and mailboxes, so it's less precise. And we see that the graph and the list abstractions are the most precise one. So basically, we want to minimize this number of spurious elements. We also compare with the state of the art. So Meuter is a tool to verify errors in Orang programs and mailbox bounds. And we run our tool as well with the different abstractions to try to verify a number of benchmarks on the absence of errors and with the mailbox bounds. And we can see that, for example, on absence of errors, we can verify all the benchmarks with the graph abstraction. And with the mailbox bounds, we can verify almost all of them. There's only one that we couldn't verify with the graph. And we see, for example, that the powerset abstraction does not have a good precision because you can only verify one of them. So we have a replication package for all these experiments. So the artifact contains the instruction to reproduce the experiments. It contains the implementation. It contains the cock proofs. It contains a technical report that outlines the proof. The implementation itself is done in Scala. It analyzes scheme with an actor extension. And it contains the benchmarks as well. So to conclude, we describe how we can, by going into the concrete semantics and simplifying the interleavings that are described by the concrete semantics, we can simplify an analysis, and that using the original macro stepping isn't a safe way of doing that, and that we have to adapt it. We've seen that there are multiple ways of abstracting a mailbox, and we have seen multiple ways of doing that, and we've seen that depending on how you abstract the mailbox, you have different performance and different precision. Thank you.
So I understand that the focus of this work is on the mailbox abstraction. Yes. So this is fine. But I'm a bit confused. Your input language is a higher order language.
Yes, it is.
And I have not seen anything related to, higher orderness here.
Yeah. So so the input language is higher order. Some benchmarks use higher order features, but that's so the goal of the paper is indeed the mailbox abstractions, and because we implement this on a framework that analyzes scheme, that's why we have an actor extension for scheme. But yeah, the higher orderness is not the main goal of the paper. It's about the mailbox abstractions.
I'm also a bit confused because I thought that when you were looking at size, you were looking at what is the maximal length of a mailbox. Yes. At any time. And I have not seen any examples, or can you report on examples where you were able to deduce the maximal length and how precise it was?
So the examples remain small. And it's basically an example where we send a number of messages to different actors, and we are interested to find what is the maximal bound on a certain message.
So what were they? How precise were your results?
What size were those?
How precise?
How precise? Well, we have. Yeah, so we don't have that many benchmarks. We have 7 benchmarks, and we could verify the bounds. Well, we have 7 for the bounds, and we could verify the bounds on.
Do these benchmarks that you have involve any calculations, any numbers? There are examples, for instance, when you have got a ring, and in the ring everybody sends, every actor sends a message with a number to the other actor, and the actor decrement sends it further, and so on. So something that involves also some calculations rather than just the actors send messages to each other.
Maybe we can look at the benchmarks. I can show you the different benchmarks, and because right now I cannot just think of the benchmark precisely.
Great. Very nice work. Last year, Midgard, Nielsen, and Nielsen published a paper at PPDP about lattice valued regular expression abstractions for analyzing message passing programs in the context of Go.
Okay.
So, well, your model seems more like a push-down automata to me. So could you please elaborate on the expressivity of your approach comparing to Midgard et al.'s approach, and like what the abstract domain is good for in comparison to theirs?
Do you have the name of the paper? Because I don't like.
It's called lattice valued regular expression domain for analyzing message passing programs.
I haven't seen it I think, so
okay.
It's hard to say that now, but I will look at it. If you can maybe send me the reference.
I will.
Thank you.
All right.
So we know that the number of different possible messages is finite. So we know that the number of nodes in the graph is finite. So it's yeah, exactly. 1 node per abstract message, and because of the abstraction, number of messages is finite.